Atoms are the fundamental building blocks of matter, the tiny units that make up everything we see and touch. But what holds these minuscule particles together to form the incredible diversity of substances we encounter in our daily lives? How do these basic units combine to create the vast array of materials, from the simplest gases to the most complex organic compounds? The answer lies in the captivating and intricate world of chemical bonding, a fundamental concept in chemistry that explains how atoms stick together. Chemical bonds are the forces that hold atoms together in molecules and compounds. These bonds are the result of interactions between the electrons of different atoms, creating a stable arrangement. They are the glue that binds atoms, giving rise to the air we breathe, the water we drink, and even the complex molecules of life itself. Without these bonds, the essential molecules that sustain life would not exist. Understanding chemical bonding unlocks a deeper understanding of the universe's chemistry. It allows us to comprehend how atoms come together to form the substances that make up our world. It reveals how elements interact, why materials have different properties, and how life itself is possible. The type of bond formed between atoms determines the properties of the resulting material, influencing everything from hardness to electrical conductivity. Without these bonds, the universe would be a chaotic soup of individual atoms, incapable of forming the intricate structures and substances we know and depend on. The beauty and complexity of the world around us are a direct result of these fundamental interactions. Imagine sodium, a highly reactive metal, encountering chlorine, a toxic gas. Individually, they're quite dramatic, but together they form something we sprinkle on our food table salt or sodium chloride. This magic trick is ionic bonding. Sodium, feeling generous, donates an electron to chlorine. This turns sodium positive, now called an ion, and chlorine negative, also an ion. Opposites attract, right? The positive sodium ion and negative chloride ion feel an irresistible pull towards each other, forming a strong ionic bond. This bond creates a stable crystal lattice structure, which is what we know as salt. Not all atoms are as giving as sodium. Some prefer to share electrons rather than give them away entirely. This sharing is the essence of covalent bonding. Covalent bond can be polar, unequal sharing of electrons, or non-polar, equal sharing of electrons. Think of two hydrogen atoms, each wanting a full set of electrons. 2 is the magic number for hydrogen. Instead of one hogging the spotlight, they decide to share their electrons. This shared pair of electrons orbits both hydrogen nuclei, creating a stable and electrically neutral molecule of hydrogen gas, H2. This can form single, double, or triple bonds depending on the number of electron pairs shared. Sharing electrons in a covalent bond isn't always equal. Sometimes one atom hogs the electrons, like a bigger kid with a toy. This creates a polar covalent bond. Water is a prime example. Oxygen, being larger and more electronegative, pulls the shared electrons closer to itself than the smaller hydrogen atoms. This unequal sharing doesn't create ions, but it does give oxygen a slight negative charge and hydrogen a slight positive charge. These partial charges make water a polar molecule, like a tiny magnet, influencing how it interacts with other molecules. Section 5. Metallic bonding, a sea of electrons. In this section, we will explore the fascinating world of metallic bonding, a unique type of chemical bonding that gives metals their remarkable properties. Metals are shiny, malleable, and excellent conductors of heat and electricity. These characteristics make them indispensable in various applications, from construction to electronics. These unique properties come from metallic bonding, a type of bonding unlike any other. Unlike ionic or covalent bonds, metallic bonds involve a sea of electrons that are not bound to any specific atom. Imagine a metal, like copper, as a giant apartment building for electrons. The metal atoms are the apartments, and the outermost electrons are free to roam around the entire building like nomads without being tied to any particular atom. The metal atoms are the apartments, and the outermost electrons are free to roam around the entire building like nomads. This freedom of movement is what gives metals their unique properties, such as electrical conductivity and malleability. This sea of delocalized electrons creates strong attractions that hold the metal atoms together. These attractions are known as metallic bonds, and they are responsible for the cohesive structure of metals. The free movement of electrons explains why metals are such good conductors. The electrons can easily flow and carry electrical current or thermal energy. This is why metals are used in electrical wiring and heat exchangers, as they can efficiently transfer energy. Understanding metallic bonding helps us appreciate the versatility and importance of metals in our daily lives. From the buildings we live in to the devices we use, metals play a crucial role in modern technology and infrastructure. Section 6. Hydrogen bonding, water's life-giving secret. Water, the elixir of life, owes its remarkable properties to a special type of bonding, hydrogen bonding. This unique bond is what makes water so essential and versatile in nature. This bond is like a weak attraction between molecules, not within a molecule. Unlike the strong covalent bonds that hold the atoms within a molecule together, hydrogen bonds are more like gentle connections between separate molecules. Remember the partial charges in water? These partial charges are crucial for the formation of hydrogen bonds. The slightly negative oxygen of one water molecule is attracted to the slightly positive hydrogen of a neighboring water molecule. This attraction forms a hydrogen bond, creating a network of interconnected water molecules. These hydrogen bonds are weaker than ionic or covalent bonds, but they are mighty in numbers. Despite their individual weakness, the sheer number of hydrogen bonds in water gives it extraordinary properties. They give water its high boiling point, surface tension, allowing insects to walk on water, and its ability to dissolve many substances, making it a vital solvent for life. This is why water can support so many life forms and is involved in countless biological processes. From the ice that floats on lakes, providing insulation for aquatic life, to the steam that powers turbines, water's hydrogen bonds are at the heart of its versatility. Understanding these bonds helps us appreciate why water is truly the lifeblood of our planet. Section 7. Van der Waals forces, temporary attractions. Even noble gases, those loners of the periodic table, experience fleeting moments of attraction. These are van der Waals forces, the weakest type of intermolecular force. Imagine electrons constantly buzzing around an atom. At any moment, there might be a tiny imbalance in electron distribution, creating a temporary dipole, a fleeting positive or negative region. This temporary dipole can induce a similar dipole in a neighboring atom or molecule, leading to a weak short-range attraction. These forces are weak but become significant when many occur together, like the gecko's ability to cling to surfaces. Section 8. Dipole-Dipole interactions, polar playmates. Polar molecules, like water, have permanent dipoles due to unequal electron sharing. These polar molecules can attract each other, just like magnets. The positive end of one polar molecule is attracted to the negative end of another polar molecule, forming a dipole-dipole interaction. These interactions influence the physical properties of polar substances, such as their boiling points and melting points. Section 9. Other minor players, a quick look. Several other types of bonding and interactions play a role in the intricate dance of atoms and molecules. Pi bonds, involving the overlap of p orbitals, contribute to the stability and rigidity of double and triple bonds. Coordinate covalent bonds form when one atom donates both electrons in a shared pair, and hydrophobic interactions driven by the aversion of non-polar molecules to water are crucial for the structure and function of biological molecules like proteins. Section 10. Conclusion. Chemical bonding is a symphony of forces, from the strong and enduring to the fleeting and subtle. These bonds, in their magnificent diversity, orchestrate the interactions of atoms and molecules, giving rise to the astounding complexity and beauty of the material world. Understanding these bonds is key to unlocking the secrets of chemistry, materials science, and even the very essence of life itself. As we delve deeper into the world of atoms and molecules, we gain a profound appreciation for the elegant and intricate ways in which matter interacts to create the universe we inhabit. So this is it for today, guys. If you have any questions or thoughts on the video, comment down below. And don't forget to like the video and subscribe the channel for more such amazing videos.